All right, should we begin?
Yes.
Okay, good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Philip Westmoreland. Professor Westmoreland completed his degree in chemical engineering at the North Carolina State University, followed by a master's degree at the Louisiana State University, and then a PhD at the Massachusetts Institute of Technology. Currently, he's a professor at the North Carolina State University and is the director of the Clean Energy Smart Manufacturing Innovation Institute. His research interests lie on the area of energy, applied theoretical and computational chemistry with a focus on reaction kinetics, and polymer and biopolymer decomposition and flammability. He has published over 120 articles, 5 books, and presented 334 papers and posters in conferences. He has also supervisioned 25 PhD students and 12 master's degree theses, besides 7 postdoctorate researchers. So once again, welcome Professor Westmoreland. Thank you so much for being here with us today, and please feel free to start your presentation.
I greatly appreciate the invitation and the chance to share with you description of not only work that we've been doing, but work that's been going on at the interfaces of quantum chemistry, molecular simulation, statistical mechanics, classical thermodynamics, and many different sorts of applications. I'm going to subtitle this Reaction Kinetics because at heart, I'm a reaction kineticist conducting experimental and computational theoretical work as well. But I want to look at 3 particular themes today. One is going to be looking at gas kinetics. That's a natural, easy place to frame what we're talking about. And of course, it's incredibly relevant for atmospheric chemistry, for combustion, for industrial processes, for many different practical applications. I then want to shift to look at condensed phase pyrolysis of polymers. For synthetic polymers, we have different reasons why we might be interested in doing that. One is dealing with polymers in a recycled sense. These wonderfully durable materials are frustratingly durable when we get ready to dispose of them. We can also worry about flammability of those polymers. The same sort of chemistry applies. As far as biopolymers, we're interested in how we make bio-oils as energy sources, as chemical feedstocks as well. Then I'll have a few remarks on work that we've done with organometallic chemical synthesis of polymers that to show that we can only tear down, but we can also build up. Again, quantum chemistry is at the root of many of the things that I have to say here because we're interested in kinetics and we need that. 20 years ago, there was a study that I got to lead, an international comparative study that is still quite interesting to look back and examine because it was taking stock in 2000, 2001 throughout the entire world of how molecular materials modeling was beginning to be applied. We had reached a number of milestones that made quantitative results much more feasible. Ironically, within chemical engineering, it was industry that was beginning to use it more than academics. But in the early 90s, it became more and more apparent that there were practical applications. There was a large molecular simulations community that had built up within chemical engineering, not so much quantitative as trying to get the qualitative, semi-quantitative information about how properties were affected. And we needed force fields to do molecular simulation. So there was the attitude, oh yeah, we need quantum mechanics so we can get force fields. We're a much more sophisticated, advanced level now. These are all expected tools. Molecular simulations have become much more quantitative. Quantum chemistry has become not only more quantitative, but able to handle bigger materials as well. There are two different ways, though, typically that we talk about. And again, I'm talking about kinetics, but we have to talk about it in terms of thermochemical kinetics. Two natural ways to start off. One would be the sort of classical multi-scale model, looking at length scales versus time scales, and the split of thermodynamics into continuum thermodynamics, where we don't have any molecules at all, to statistical mechanicals, where we have molecules, but somebody has to tell us the information about what's going on with the molecules. Well, in principle, all that information lies in quantum mechanics. That's 0 Kelvin energies, and we can use that to get optimal structures, to look at perturbations from those optimal structures and getting frequencies, to get transition states as well. So these red arrows signify that how we normally use these is by passing information, often by simply passing parameters to be able to use. There are not too many continuum thermodynamics properties we can get out of quantum mechanics, except dipole moment is one thing very naturally you can. What about isolated molecules versus molecules in an environment, a solution of the light? Again, we can handle that rather nicely now. Another point of view, though, is to look at it from the standpoint of structure. And again, thinking of this 0 Kelvins sort of aspect, if we look on the left with the electronic structure theory at 0 Kelvins and going up, dealing with more and more heat, the electronic structure can't deal with that unless you use statistical mechanics to get specific heats and extend it, while molecular simulations seems to thrive at high temperatures, things bopping around and interacting with each other. Again, they're the different sort of classical methods, where the so-called ab initio methods, my friend and colleague John Popel hated the use of ab initio because he says it's built on empirical descriptions of wave functions, empirical exchange energies for density functional theory. And yet the idea that we're looking at things that have fundamental roots is the reason that that name is so common. Popel actually started off working with semi-empirical molecular orbital theory, something that still finds use, but all of them depend on having basis sets, description of the electronic orbitals that exist, and then are used in these different methods. On the other side of the statistical mechanics river, we have Monte Carlo, molecular dynamics, molecular mechanics simulations, where they, again, depend on force fields, potential energy functions. All these are connected, though, by StatMech when we come down to getting actual properties there. And there are a few methods. I'll mention a little bit more about Carparello and VASP later on. So when we talk about thermochemical kinetics, we then talk about relying on quantum mechanics, particularly at the transition state structures and energy barriers, computational quantum chemistry. The statistical mechanics not only get thermochemical properties, but for the very foundations of transition state theory to relate that information to kinetics of actual molecules in systems. And then molecular simulation proves invaluable for looking at the phase effects, the effects of atomistic environments as well. So inevitably, we also draw very strongly from measurements, continuum theories, and ideal extrapolations. Ideal gas law is a terrible lie if you look at sort of first principles, but it's the key to all of classical thermodynamics. It's maybe the most valuable equation that we may have in there. So these sorts of idealizations are crucial. In addition, I would cite gas kinetics theory. We'll talk about how collisional energy transfer data come into play and the beginnings of being able to predict those. The use of population balance methods, so-called master equation theory, to look at reactions, and to do quantum chemistry of solvation, the whole family of polarizable continuum methods, and then in quantum chemistry, compound methods, where we take different model chemistries and extrapolate to the ultimately high level of theory, the ultimately high level basis sets. And onion, which is a layering method, thus the acronym for it, where you are able to take high level calculations and lower level calculations on the center reactive region, and then do low level calculations of a larger domain and extrapolate to what a high level result would be at the full domain. So gas kinetics, as I said before, is a natural place to start because of its importance, because we can deal in an ideal gas with relatively isolated molecules. So, for example, if we want to talk about biofuels like dimethyl ether, we can sketch the molecule, we can draw it with different sort of space filling models, and we can do experiments, so-called one-dimensional flat flame, sort of flame that would propagate through a box in a flat fashion. If we had a flat ignition source like a laser sheet, can actually be simulated in the laboratory by burner supported flames or by propagation spherical reactors. If we talk about conditions that are slightly fuel rich, in other words, stoichiometric mixture at 1.0 equivalence ratio, 1.68 would have 70% more fuel than needed for stoichiometric combustion. And we can get a dizzying amount of data. And now we can begin to do remarkably good. I mean, I look at it now, and this is about 10, 11, 12 years old, and say, well, we can do better than that now. But then, and really since the 1980s, we've begun to be able to handle these very complex situations where we see the dimethyl ether predicted quite well, and then the oxygen consumption. Interestingly, in these early parts, oxygen and dimethyl ether aren't reacting. Diffusion is contributing to dilute them progressively less and less as they come back towards the surface. Argon is inert, but it's also being diluted as products are formed, things like CO and hydrogen, which react to CO2 and water, and many, many more species. So we can test these things. We can build detailed kinetic mechanisms for these and more complex molecules. Tetrahydropuran is the ring structure that appears in so many pyranose saccharides like glucose. And here we have, detailed measurements of these sort of major species and then of different intermediates going from excellent to respectable sort of predictions. Where did these detailed mechanisms come from? What about even more complicated systems? Well, the logic of putting them together for, say, for tetrahydropuran is we can look at classes of reactions, beginning, say, with abstraction, forming radicals that can decompose in different ways, radicals that can react with their environment. So I want to back up to a simpler model that depicts the types of reactions very cleanly, just methane, where we know that thanks to work that Jürgen Varnatz and others did in the 70s and 80s, they began to build elementary reaction models. They were drawn from empirical data. There was no computational chemistry that they were really using at that point. But the idea actually helps us understand how computational chemistry is useful here. The idea that methane goes to methyl, we can show here the structures of them, and by abstraction forms a methyl. Then the methyl can react with O, some sort of mysterious fashion to make formaldehyde, and then by abstraction lose a hydrogen to make formal radical. Turns out by decomposition or by reaction with O2 can make CO, which reacts by another mysteriously, how do I get from CO and OH to CO2? We'll talk about that. The simplified expressions typically is using the Arrhenius expression, where I have to point out the correction that chemical engineers have to make to chemists all the time. that is not moles per cubic meter per second. It's not concentration per ton. That's a reactor expression. We're talking about moles per second of change normalized over a volume, normalized over a surface, normalized over some region, and simple mass action equation with concentrations, or better yet, activities, and an Arrhenius form expression, or Arrhenius's colleague, von Kuai, developed this sort of 3-parameter expression for the rate constant with the T to the B term in it. If we have a constant change of energy from the transition state, from the reactant to the transition state, factoring out 1 degree of freedom through statistical mechanics, we obtain for constant delta S and delta H transition state an Arrhenius type behavior, which does have this power law form of temperature in it. Again, if this is constant and delta H is constant, and there's a little bit of RT. Delta H is typically much bigger than RT, so it's almost negligible, but it has to be in there. It's probably better still in a thermochemical sense to think of it as E kappa T over H times e to the delta minus delta G transition state plus RT, because there's a compensation effect as the entropy rises with temperature or changes with temperature due to specific heat, and the delta H changes in the same direction, but one is E to a positive, one is E to a minus, so they end up compensating, offsetting each other. So the simple principles behind these, I think if we just step through these same reactions very lightly and look at how they're formed, we see the sorts of steps and how computational chemistry and thermochemistry play in. So just with that first one, simple abstraction of a hydrogen from methane. By analysis of many reactions, we can generalize and say that there are 2 different ways we can classify reactions in gas kinetics and much of condensed phase chemistry. They're abstractions of H or halogens only, not really anything else. They're association or the reverse reaction decomposition, or isomerizations, most of which involve some sort of association or abstraction, but internally. The types of reactions in terms of electronic structure, though, are either radical neutral species, ionic species, or we have molecular paracyclic reactions that can occur. Within what we're talking about right here with this simple combustion set, they're all radical chemistry. Molecular reactions, paracyclic reactions do begin to show up more than people had realized. But my focus here is just going through these general classes. So again, hydrogen abstraction. And if we put in simple energy diagram, you see abstractions often are fairly small barrier here, 19 kilojoules per mole, about 4 kcals per mole, but exothermic. Well, if we're looking in the exothermic direction, because of course, methyl can in principle abstract a hydrogen from water as well, but we have a 64 kilojoule barrier to overcome to do that. If we compare to data here from the NIST chemical kinetics database, which I happened to check this morning, it seems to be not working, but anyway, NIST has this very nice database where you can plot up all the data that they have in their records, and you see, well, it's not, okay, it's on an Arrhenius plot, but there's curvature in there. Again, delta C sub P changes with temperature. So, and for example, and furthermore, it exists. So delta H and delta S transition state change as well. But the point is that we can describe this theoretically very well now, particularly abstraction. When we get to collisionally mediated reactions, theory leans more heavily on data. For looking at methyl going to formaldehyde, this was originally, methyl was originally thought just react with O2. And when in the early 70s, the idea was found that it made 8 plus formaldehyde, people said, why? It sort of just scrambles. In fact, theory theoretical developments that I participated in ended up showing that no, there's an intermediate. It's actually an association reaction. It's a radical combination of the methyl and the O atom, the diradical O atom, to make a methoxy. That methoxy can decompose a beta scission, or radical beta scission, just the reverse of radical addition, to make H plus formaldehyde. And the energy diagram explains it, because you're starting out with methyl and O at a very high energy. You're making a bond. It's still a radical species, CH3O, but you're 90 kilojoules above that base level of methoxy, while it only takes about 25 kilojoules to break out and form the H plus formaldehyde. And the collisional mediation is important here too, because this nascent CH3O that's formed is very high in energy. It's not instantly at the bottom of the well. In fact, it can only get to the bottom of the well by being collisionally relaxed into a Boltzmann type distribution. And well before that happens, at any reasonable pressures, it decides it would rather go and make HM formaldehyde, just skim over that barrier. The data support that. You see a really constant number, except at the highest temperatures, where you can actually see this nascent CH3O also show a reverse reaction to methyl plus O, decreasing the net rate forward to H plus formaldehyde. Well, that is called a chemically activated reaction, a chemically active association with decomposition, because the high energy of this methoxy is not due to thermal energy, or not just due to thermal energy. Methyl and O bring in thermal energy of their own, but it's largely due to the chemical energy that it has relative to the thermal distribution. In effect, it's a reaction over a well. There's an interplay here. I'll diverge to look at H plus O2, because that's the classic explanation for why we even have a flame. H plus O2 making HO2, which is a radical, but a rather sluggish one, versus O plus OH, which is chain branching. One radical H gets you two O and OH, and O atom is a diradical, so a lot of boost there. Well, in fact, H plus O2 isn't two reactions. It's one chemically activated association reaction, in this case with the products being slightly endothermic. But the nascent HO2 star can revert to H plus O2, be stabilized, or split apart to make O and OH. Because it is endothermic to go to the O plus OH, this HO2 is, as you raise temperature, it begins to want to go more to H plus O2, and you see a fall off behavior. The rate constant actually decreases. But when we look at it here on a third body, treating it as a termolecular reaction, see it's more or less a constant value, dropping off somewhat with increasing temperature, that is, we go to the left. On the other hand, the O plus OH, you see that putting back on a biomolecular basis, the HO2 formation, it's dropping off here at 1 atmosphere, while H plus O2 is taking off. So this transition about 1,000 kelvins is really key, because that's where chain branching comes in. The next step, simple hydrogen abstraction, where I show OH pulling off a hydrogen and to make, should be water, and formal radical. But then the CHO, we can recognize now it's a radical decomposition, or with O2, an abstraction. And then the key reaction that creates global warming, well, doesn't create global warming, creates the CO2 that we worry about so much. Again, looks like another scrambling reaction, but is in fact a chemically activated reaction over a well, a radical addition to make HOCO, HOCO, which decomposes to make a radical H and carbon dioxide. Looking at this sort of diagram, you see again the well in the middle for HOCO, and entry and exit barriers that are about the same. So setting up a competition between reversion to reactants or proceeding to products, that is really important because this is a different energy scale. Going from CO plus OH to H plus CO2 is very exothermic. And that's the reason we get heat out of flames to a large extent. This is the reason we get usable energy from combustion. When we look at the energy diagram, this is terribly non-Arrhenius, but now looking at it from a molecular sense, you can see at low temperatures where there's successful collisional mediation, making HOCO that becomes less and less favorable. As we go up in temperature, bang, it takes off and wants to go all to H plus CO2. In addition, having this sort of broad insight allows us to do more sophisticated quantum chemistry calculations that explain. So from our CO plus OH to H plus CO2, we can see that actually there's a preliminary van der Waals complex that turns out to be very common. It becomes very important in kinetics at lower temperatures, which is a region of technical interest, as it turns out. Furthermore, we find that the HOCO actually exists in states that are trans and cis that are separated by a respectable energy barrier to the transition, but it's only the cis that can decompose to make the H plus CO2. Furthermore, there's a symmetrical intermediate, a Kriege type radical here. That's down in the well here, the C2V species. But it's accessible, but with more difficulty by this chemically activated route. If you do make it by this or some other means though, say H plus HOCO coming from here, it has an easier step to go to H plus CO2. So despite all the very complicated sort of kinetics data that I just showed you in the previous slide, there's so much rich detail that we have begun to ferret out in the last 15 to 20 years using computational quantum chemistry and reaction theories that can handle these sorts of very non-Arrhenius sorts of behaviors. We apply them to things like biofuels. Biofuels are oxygenated, but many of the same reactions occur. Here's a paper we did in 2010 with my colleague Katharina Kossi-Hunghaus at Bielefeld, where we're looking at the data from this molecular beam mass spectrometry technique using vacuum UV photoionization, but then proceeding on to look at the detailed kinetics there that are described there and in our later papers. Likewise, fluorinated compounds are a big concern around the world right now. There's a big shift. Well, let's see, 30 years ago, there was a shift from using halon as the ideal fire suppressant for non-aqueous, electrical systems, for example, aircraft, where you can't flood the aircraft, you can't put toxic chemicals in. CF3BR was wonderfully non-toxic, but it was not so good for the ozone. In fact, it was worse than chlorofluorocarbons. The substitution was substantially to go to hydrofluorocarbons because those would not survive passage through the troposphere, getting to the stratosphere. Now it turns out that, yeah, that's good for the ozone, but it turns out they have bad global warming potential. So in the last 10 years, there's been an effort to shift to HFO 1234YF. Here in the circle, basically propylene with a fluorine on the central carbon and 3 fluorines on the methyl group. We were approached by DuPont, which then became Chemours, to develop a reaction mechanism based on my having worked at NIST to develop the standard mechanism for smaller C1 and C2 fluorocarbons and hydrofluorocarbons in the early 90s. So we began using this same logic that I've just described to you for simpler reactions. We can have homolytic scission, or we can have elimination reactions. These are actually paracyclic elimination steps, but we can use quantum chemistry at low levels, at higher levels like CBS-QB3, G4 and G3 calculations to determine that the HF elimination rather than the HCF3 is most favored here. Then we can go on and fill out the rest. It looks pretty dizzying, but if you look at the first row, what are we talking about? We're talking about abstractions of hydrogens across the top by any old radical or by H, O, or OH. And then we're just talking about the decompositions, and in some cases, bimolecular reactions with the O atom to make C1 and C2 fluorocarbons. This was successfully verified in looking at the very limited data that were available. So now we're doing work with the U.S. Environmental Protection Agency to try to develop incineration data for perfluoroalkyl substances and their water-soluble salts. Now we've got to talk about phase effects, and quantum chemistry doesn't help a whole lot with the phase effects. So let's shift to polymer pyrolysis, the second part. Again, I said before, synthetic polymers, recycling is a reason to look, one of several. And if we're talking about biomass, then making bio-oil from woody lignocellulosic materials is important. So this diversity of synthetic polymers is wonderful. The durability is wonderful and just makes it a problem to get rid of. So many industrial organizations, Eastman, Dow, so on, and the International Council of Chemical Associations have asked that there be a global agreement to end plastic waste. Yes, we've got a lot of plastic waste in our dumps, which are the resources of the future, the mines of the future, but we also have to deal with controlling plastic waste and finding some way to reach a circular economy where it can be reused and not just build up in the ocean. In the case of thermoplastics, they're often polyolefins, so those can melt and be broken down thermally into monomers. It's a little harder if we talk about thermosets because they're condensation polymers. We have to find some hook. Our work, ironically, with biomass indicates that in many cases, we're talking about using homogeneous catalysts as simple as the OH groups in water to do destruction of those materials. Again, this ties directly to polymer flammability because polymer itself doesn't burn, it decomposes, but its pyrolysis products burn. So if you make a lot of pyrolysis gases that are flammable, you've got a flammable polymer, which you may not want, or say for a propellant, you may want to have. In the case of lignocellulosic biomass, the name implies that it's got cellulosic, actually cellulose and hemicellulose content, as well as lignin. Looking at sugarcane bagasse, you see not quite equal portions, but comparable portions of those three plus ash. Plus there are these cell contents that can be removed by various detergents, but we're talking about the biomass itself, and then the cell walls are where this lignocellulosic material is. That's why wood has to be cured for use. But within those cell walls, we find this intricate structure of these cellulosic microfibrils, crystalline structures that are crystalline because of the stereoregularity of the glucose and cellulobiose components that make it up, and the hydrogen bonds that occur between them. So we use molecular simulation to try to understand the phase transition that's there, as well as the phase transitions that happen in synthetic polymers as well. A larger goal is then understanding the rates, products of decomposition of the fractions of whole biomass, their components of whole synthetic polymers, and so on. Experimentally, we have really neat new tools in the last few years. Thermogravimetric analysis, simply weighing while you heat, is a long-standing technique. I used it back in my master's thesis. stuff into your delicate instrument. On the other hand, by combining them, we can get both heat release and reactions that have thermal signatures but no mass change, as well as the things that do have mass change. Also with flash pyrolyzers, and then using some of the advances in analytical techniques like two-dimensional gas chromatography with time of flight mass spec. This instrument, we have this looking at a whole bio oil sample. You can see from the inset, it's really looking top down onto a contour plot of peaks. But we've got a primary column, and as material reaches the end of that primary column, it's cryo-focused and then shot into a second column, and the elution time in the y-axis is that second coordinate. Allows extraordinary amount of separation, 3 to 5 times more than you get by conventional GC mass spec, and with a lot of species identification. So if we look at two examples, high density polyethylene, the very regular CH2, 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 and polymethyl methacrylate, we see two extremes of behavior. This polyethylene, in terms of products, I choose to show the total ion chromatogram here first. It's a wide spectrum. This decrease actually is a decrease due to the instrumental effect. We've reached the maximum temperature in our GC temperature ramp. So these are still pretty high. It's just random scission throughout the whole molecule, breaking it up. As a result, we make alkanes, largely alpha olefins, 1-alkenes, and various dienes. When we look at the mass signature in black or the thermal signature, we see complementary information. We see the heat of melting here, the phase transition more fairly. And we also see 3 different locations where reactions are occurring, where you can only see one big mass loss and look at the mass curve. Again, the blue or more shaped behavior is the heat flow that we're measuring. So we can extract reaction kinetics from this to make use of. And furthermore, by combining that with the products, we can make these mechanistic insights empirically that it's random chain scission. At the other end, with polymethyl methacrylate, if it's lab synthesized polymethyl methacrylate, monomethyl methacrylate is all that you get. Basically, it implies that there's a hydrogen abstraction and then it just unzips beta scissions to the monomer. And yet we look here at the mass plot, we see there's 2 different regions in the mass plot and also in the thermal plot where reaction occurs, and a smaller phase change signature over here. A bit of a drifting baseline, but again, there's kinetics insight into here, but what we really need is a Maxwell's Demon to get in to look at it. And is that quantum mechanics? Well, in some cases it is. At the recent COBEC meeting, I gave a plenary talk describing our 2012 discovery that the breakdown of cellulose is actually homogeneous catalysis. It's homogeneous catalysis by not OH radical, but the OH functional groups that the molecule is full of. In the inset of this journal cover, we show the OHs, but in this diagram that I'm going to animate in just a minute, I've stripped off OHs from 4 of the carbons just to make it more visible, but there are OHs everywhere. In this case, I'm showing an animation for glucose, again, the monomer of cellulose. And this H that I show right here with the dashed line going to it would actually be another glucose molecule, but for sake in visibility, I'm just going to use that. Glucose has this pyran ring, this 6-membered ring with an oxygen ether, and it has a CH2OH on the side. So what we can do is use water, but it's really HOH to show how the reaction occurs, where this could be, instead of an H, could be another glucose, it could be another cellulose chain. And subsequent work by Matt Newrock and Paul Dallenower proved that that is the case. But let me just show you what happens. So as we start off, what we end up seeing is that there's a paracyclic molecular transition state that begins to form. And the OH bond breaks here as the H comes from this OH group. One of the H's is donated, it comes off as water. This H here, remember, was standing in for whatever the moiety was that was connected to the oxygen here. And it comes off and leaves an OH behind. And we end up forming a double ring species, a levoglucosan type structure where there's a 5-membered ring and the 6-membered pyrene ring itself. So the insight here is that it's a catalysis by paracyclic molecular reactions, not by transition metals. And the reaction is not simply a radical scission breaking the bonds apart. These sorts of events happen in a number of condensation polymers. In polyolefins, we see signatures of other things. So here, for example, with polystyrene, the empirical data give us an activation energy that's very close to the bond energy of the polymer chain, suggesting that it's really being driven by ripping the CC bond apart somehow. There's a problem, it's condensed phase. So we'll talk about that in just a moment. Nevertheless, if we talk about polymethyl methacrylate, I showed you the different regions there. It turns out there's another low temperature region where the activation energy is very close to the bond scission energy, but then there's a nearly zero activation energy region in the first region, and then an activation energy that's very close to the radical beta scission activation energy. Those empirical pieces of information give us ways to do molecular modeling that can give more insight. In some cases, like polyguanidine, polycarbodiimide, we could see that there's an internal paracyclic reaction that splits the chain. In this case, it leaves a cyano group at one end and simply a diamide with amine type group at the other end. So in some cases, yes, we can get paths, we get transition states, but polyolefins end up being a problem, mainly because how do you get temperature in there that's different from the temperature that everything else is seeing? In addition, homolytic scissions don't have electronic maximum in energy. They're just monotonically increasing. In the gas phase, that's the same, but in the gas phase, you have rotational energy that can come in and add and give you a small but real energy maximum. So how do we break the CC bond? And how do we get enough energy localized into a bond to get it to break? Turns out, I think reactive molecular dynamics is really the key. That's something that's really breaking across our field. It's the typical sort of overnight success, been building for 20 years, 30 years now. But in particular, Mark Neiden had pioneered this work back in the mid-90s, saying, okay, this is a fool's errand. There are a lot of motions going on that have to be described by molecular dynamics compared to the rare reaction event. But let's go ahead and do it anyway. We featured that at AICHE in the 1998 topical conference that gave birth to AICHE's Computational Molecular Science and Engineering Forum. It's seemed groundbreaking then, it's still groundbreaking. There are other people developing reactive force fields, which have also been very successful. What I'm going to show you right here, though, is work that Stolyarov, a professor at University of Maryland, did with me as a postdoc when we began working with Mark. Again, the idea is that you're using conventional MD, but you're applying a bond breaking making algorithm. How can we declare that bonds actually break? In conventional molecular dynamics, you might think, well, we only have pure homolytic scissions as things get to the full energy and can break apart. There's a reason why that's not good enough. But we could also adaptively apply this algorithm using a fractional bond order criterion to do it. In addition, the equilibrium force field has to be modified or otherwise adapted rather than, say, a quadratic stretching mode, which people wouldn't generally use now anyway. but the idea of having a breakable stretching potential is necessary if you're going to break and make bonds. Furthermore, there are other modes that are also coupled to the bond breaking. Just think of methane going to that flat methyl group, and you get these internal changes as we adapt. Furthermore, Ken Smith, who did his doctorate with me when I was at the University of Massachusetts, had found that it was necessary to put an electronic mixing function. I'll come back to that, but it was an empirical fit to quantum mechanical energies. A very popular reactive force field now is ReactFF, both popular because it is pretty widely applicable, but also because it's been implemented in the software lamps that many of us use. The idea is this, though, I mean, basically for all of them, is that we have a potential vibrate. And if they are high enough energy, they can vibrate completely apart, but at intermediate levels, the vibration can weaken the bond enough to be susceptible to an attacking third body, say for an abstraction, where we see a transition. Of course, transition states don't have cusps where these potential energy surfaces meet. There's a mixing of the electronic wave functions that goes on. So this is an engineering description, quite frankly, of what's going on that Smith developed by putting in this mixing field to capture the transition state energy more accurately. And it's probably a lot easier to show a picture, even for sophisticated people in molecular modeling. Here, this is part of this is the central cell with a 15 mer of polymethyl methacrylate with periodic boundary conditions applied. So the greens, just for visibility, are carbons, reds are oxygens, and these little grays are hydrogens. So let me show you what happens in this animation. So we see motions, we see rotations trying to happen through here or happening. We see bonds stretching, we see bonds compressing, tightening up. Right here, we're going to see a bond stretch apart, but then come back together because the radicals that are formed have to get far enough away from each other to be able to continue reacting. So over here in this part of the molecule, we are going to see it pop off. So there we pop off a part of the monomer. We see it actually unzip to make CO2 and methyl, while the rest of the molecule is beta-scissioning away. Number of insights that come out of this. It turns out let me stop it. If we do larger simulations, we can find rather quantitatively accurate results from that. The more than just the quantitative predictions, though, is what is actually going on there. What's going on is that back in the previous slide, what we were seeing, as I said, bonds were being stretched and compressed, but what happens is that polymers with side groups, like not HDPE, polymers with side groups can have entanglement of the side groups. And because of that, when stretches happen, it may get locked into that stretch. Of course, it can get locked in compressing too, but that locking is like a ratcheting motion and is a way of accumulating energy in bonds that can then break as a result. Again, it's not just the breaking, they have to migrate away from each other as well. But that is what accounts for the quantitative accuracy, and that key insight comes out from doing the molecular dynamics with reactions. We're also applying ReactFF in lamps to look at breakdown of monosaccharides and polysaccharides. So here I just show Xylose, work with oligomers of xylan as well, supercomputer. But again, xylan is important because it's an important component of hemicellulose that we saw makes up about a third of lignocellulosic biomass, and then tested against our experimental data. we're not just predicting, we're testing the reactive molecular dynamics to see how well it can do, because that would really help us as reaction engineers. To do it, we have to generate starting sets with sort of conventional techniques of generating cells at different densities that can be applied with periodic boundary conditions. So even here you can see at the edges, parts of molecules are cut out, even though they show up on the other side. That presents a challenge to following what is going on. So for example, we developed software that can pick off the reacting species just before and after the reaction event, and determine the reactants and products that are present, even though it's in the middle of a very full sort of box that's going on there. So using multiple runs, we can measure kinetics and identify products. So here for Xylose itself, we find very nice Arrhenius behavior, even with only 5 trials at each temperature that's there. Again, these error bars are 1 sigma, not 2 sigma. So it's a little bit harder to see with 2 sigma error bars, but then more trials would tighten that up. Likewise, using the software from the previous slide to identify species, from smaller species like water, formic acid, ethanol, to much larger species, including glyceraldehyde, methanediol, and the linear, the non-cyclic, acyclic xylose structure as well. We can compare quantitative results where here I did it, the blue is going to be our data, the red, the middle bar is from the LAMPS Reacts FF, and the reaction mechanism generator developed by Bill Green of MIT and his protege Richard West at Northeastern, also doing predictions. And we see they're fair agreement. You wouldn't say it's great, but it's fair agreement in terms of the yields, and shows some interesting agreements where, again, now we have a Maxwell's demon we can look in and see what's going on and tease apart, does this make sense or not make sense? So flaws and yet power as well. One flaw in the gas kinetics is vibrational energy needs to be quantized, but it's not when you use a force field. Furthermore, at high temperatures, harmonic oscillator representations fail. So we have to sort of run hot enough to be near continuous density of states so that quantization doesn't matter, and then cold enough for the oscillators to be pretty harmonic. This mixing of wave functions that I mentioned before was Ken Smith's mixing function, a fitting approach. In principle, we could use quantum chemistry at every step, but again, there are a lot of motions going on. If you're talking about a trajectory calculation, one molecule coming at another molecule, whether it's for reaction or studying the amount of energy transferred in collision of certain collision rate, of intensity, amount of momentum, so on and so forth, translational to translational, translational, vibrational, 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 so on. And then finally, Carparnello and Vass by Benicio MD are terrific tools that have been used for a while now. They do use simplified electronic description, so that affects the accuracy. On the other hand, if you have surface chemistry where things are in 2D and where the reaction sites or adsorption sites can be repeated, it's proven its value, very helpful. And finally, this rare event business. I think we have to hold for improved algorithms and parallel computation to increase the calculational speed. I'm going to close now by just making a few remarks on Metalcatalysis of polymerization, showing that value too. In this work here, we know that 10 is very useful for esterification and transesterification. Simple sort of, we've got this carboxylic acid here, and we've got a diol here, and then doing the transesterification, the esterification reaction, esterification, transesterification. We can basically clip out the water, or in this case, the methanol. This N group here is a CH3 in effect. We can clip those out and make a longer chain like a polymer. including polycondensation reactions too. So again, the activity relative to other species, I've highlighted the tin in red here. Titanium has some merit, but not over as wide a region. Anyway, how does it happen? Work that is frozen. Okay, there we go. Chaz McGill, who's currently finishing a postdoc with Bill Green and about to take a position as a faculty member at Virginia Commonwealth, showed that actually in the transesterification with tin, what we have is a 4-center transition state that's, I believe, involving we think is involving 6 electrons, but 4 centers, where we form this complex, this addition complex here, but it doesn't go directly to the products of esterification or transesterification. What you see is a conversion to other structures. There are 4 different intermediates here that interconvert in the reaction scheme. But in the end, what happens is you get this restructuring of the 10 oxygen bonds that goes ahead and leaves the tin substantially regenerated, but you have this the product here changing from R3 over here to R2 over here. When we test against data, again, this works out very nicely using a couple of different tin catalysts, tin acetate and dibutyl tin oxide. And we can compare to these various sets of data and find quantitative agreement. So again, my point that quantum chemistry is very important. I must take note that these things are happening in the condensed phase, and while we can model solution effects, Chaz also found it was necessary to use explicit solvent calculations. And anytime we talk about phase changes, we have to think about molecular simulations too. So to summarize, talked about gas kinetics and the molecular steps there, talked about condensed phase pyrolysis of polymers, and a little bit about chemical synthesis of macromolecules. I have to certainly note our longstanding support from DOE and National Science Foundation in the US, more recent support from the Environmental Protection Agency and Savannah River National Lab, DuPont, Chemours, Eastman, and our supercomputer resources, the National XSEED resource, now changing names, but we used it as XSEED in NC States. And of course, I thank the organizers for inviting me. It's always a treat to tell people to talk about work that we are interested in and passionate about.
Thank you, Professor Westmoreland, for your presentation. We're now open to questions. If you want to participate, please enable your microphone or write it down in the chat and we will read it. Also, our YouTube viewers can write it down too, of course.
Thank you, Phil, for this nice presentation. It's exciting that we can use quantum mechanics more and more to understand some reactions and so on. My question is, in gas phase or in other situation, you need to know the complex state, the transition state. Sometimes you guess, and how you deal with this, because it's going to be defined in the kinetics, going to be defined for these states, and sometimes we don't know, or sometimes they're strange in somehow.
You're describing the very heart of the intellectual puzzle that consumes me as a kineticist. As it turns out, with these understandings that we have of the types of reactions that can occur, even very strange reactions, I popped up the simple reactions, H plus O2, O plus methyl, and CO plus OH as things where you can't really imagine a transition state for those. But if you follow the logic and say these types of reactions can happen, it's a radical reaction or it's a molecular reaction, or maybe there's ionic chemistry. suddenly you begin to be able to tease out qualitatively what the structures of the transition states will be. Benson's classical book, Thermochemical Kinetics, gives a number of empirical rules for estimating the structures of different transition states. But what we then do is, and most of our computer time is taking, is searching for what those elementary reaction transition states are. So you put your finger on the heart of the matter, trying to identify what the elementary reaction transition state is the challenge, although when you break it down to the elementary steps, they're much more understandable, much easier to make initial structural guess at. There are also valuable techniques. Full disclosure, I consult with Gaussian, I do short courses with them. I use Gaussian. It and other of the several other quantum chemical methods have techniques like quadratic synchronous transit methods, where you can actually start with the reactant and product and have the code searched for the maximum energy in between. Of course, it goes down to the initial point that you're making, that you have to have an elementary step first. You're muted. Yeah.
Sorry. Another question is, I hadn't never did myself this test, but if you get a reaction field and do reaction in a simple gas phase without solvent, do we get the same transition state?
When you're doing that sort of situation, you have the real life luxury of sampling all the different transitions, not just the minimum energy pathway that we find with quantum chemistry. So you find different transitions because there's different ways to clear the energy barrier. So it's actually, in principle, a much better result. Still, it depends critically on the reactive force field. George Peterson and I co-advised a student who began looking at different ways, looking at our reaction MD-FF force field that we had developed, which is an adaptation of an equilibrium force field, and comparing it to Reacts-FF, working with Audrey Van Dwijn, the person who created that. We found that Reacts-FF was prone to be giving horrible numbers if you were not close to the equilibrium or the transition state structure. So the reason we continued on our path was finding that we got better numbers because it was rooted in an equilibrium force field, not a purely fitted force field. What Audrey does now is mainly does fitting not to data, which was the original approach, but to quantum mechanical calculations. And there he can sample more geometries, and yet its potential energy surfaces for more than 4 atoms are pretty tricky. Nevertheless, this issue that you talked about, in principle, doing reactive molecular dynamics allows you to sample all the configurations that can occur, including things that aren't minimum energy pathways. Problem is the force field has to be good at all those alternative structures as well.
Thank you, Phil. Nice. Let people ask.
Does anyone still want to ask some question?
Well, of course, anybody who has follow-up questions, I'm happy to take them by email or by Zoom. And as I understand from previous Adam's presentations, it will be available on web as video also.
For sure, Professor. So our time is almost over. Oh, sorry, Professor Fred wants to talk.
As nobody wants to ask, let me ask you one more. I'm very interested in the reaction in this complex system like cellulose. But I think it's really a big problem. And you have shown that maybe you don't need to treat so big like that. If you see only a region of the, it may define everything. But for me, it's, well, this is a very complex structure in a real life. And you have several problems like diffusion, local diffusion, or if some no access for some due to some configuration of this complex molecule, so you may not have the access for some points and so on. And how to do with these complex situation that is going to be similar for polymers or some polymers.
Yes, in the case of cellulose, the regularity of it is a great assistance. I can put up this slide here. Here's just, these are schematics. Don't take them as absolute truth, but they're schematics. The point is that this great regularity that you have in the cellulose, the structures, if we go back to this structure, where we have glucoses that are strung together by 1,4 glycosidic bonds. I particularly would show the second picture because if you look top down, you see it looks perfectly symmetrically. As you rotate it around the main axis, you can see that all the oxygen, hydrogen, and carbon hydrogen bonds, or most of them, are oriented normal to that ribbon of the structure. And that indeed is what leads to all this hydrogen bonding network. That hydrogen bonding network is ideally studied by molecular simulation because the absence of covalent bond interactions that are there. And there has been interesting work done on that. Empirically, though, what we know is that until you get to the point where the cellulose loses that crystallinity, say by thermal heating, you don't get the homogeneous catalysis beginning to happen because you can't get the OHs in place near the bonds that need to be broken. So the combination of aspects there. Now, in addition, it turns out that that gives us a great insight for hemicellulose. Hemicellulose is very non-crystalline, it's amorphous, and indeed, its decomposition starts about 100 degrees lower in temperature because they're already mobile. They're already in positions where they can interact and do that homogeneous catalysis. And I think that's been the key insight we've gotten out of our hemicellulose work. It's basically the same chemistry, the same saccharide chemistry, except that the hemicellulose is intrinsically amorphous. The cellulose is not all, but a large part of it is crystalline. So the destruction of those microfibrils happens when things melt. I would add that lignin, I thought was pretty well settled as being free radical homolytic bond breaking, but there's research in China now that shows that these homogeneously catalyzed OH functional group reactions are also happening in lignin breakdown as well. So the complexity, to some extent, we can, for some cases, we can segregate. In other cases, say for hemicellulose is covalently bonded to the lignin. So you sort of have to go ahead and look at the reaction and the molecular dynamics at the same time there. But it's a fascinating avenue with a growing number of people who are beginning to probe this. Again, it's a little bit of a fool's errand just because of all the time that it takes. If you think a conventional molecular dynamics calculation for a longer time period takes a long time, Now you're trying to do these energetic calculations at every step, looking for reactions as well. And yet we see interesting results coming out that can only get better as we improve our algorithms, as we can improve our computational capabilities.
Thank you.
Of course. My pleasure.
So our time is almost over. I want to thank you everyone for the discussion. And once again, thank you, Professor Philip Westmoreland, for the presentation.
My pleasure. Thank you.
It's our pleasure. So our seminars are being recorded and posted on YouTube, and after the invited lecturers agreement, of course. Please check them out on our YouTube channel. On next week, we will not have a seminar because there will be a Congress, the FOA. And so we'll see each other now on the 2nd of June. And this is with Professor Randall Kusner. And this is our organization committee. We are responsible for inviting and communicating with the lecturers. We also handle social media, video editing, certificate writings, and hosting. Thank you all for being here today, and see you on 2nd June. Thank you.